Hello, everyone, and thanks a lot for joining me for this session talking about writing a Kotlin compiler plugin. First of all, let me introduce myself. My name is Xavier Gouchet. I'm a French staff engineer working at Jetpack. I've been writing Android apps since 2009, and I've been writing in Kotlin since 2016. If you don't know about it yet, Jetpack is a French application that has a cashback and a shopping assistant. We started trying to give customers the best price for the product they wanted, whether they purchase online or in stores. And now we're building an AI shopping assistant to let them find the best product for the needs. By the way, we are hiring. We're always looking for new engineers. So if you're looking for a career change, you can come talk to me at the end of the talk, or you can look at our Welcome to the Jungle page where you have all the offerings and lots of information about the company. Anyways, we want to write a Kotlin compiler plugin, and the first question we want to ask ourselves is why. And this is our introduction. We're going to talk about what is metaprogramming. Metaprogramming is the ability for code to actually read, analyze, and modify or generate another program. So you're not having code that runs to interact with the user. You're making code that modifies an existing program. This usually allows you to generate or modify code that can happen either at runtime or at compile time. This is not something new. This existed for a long time, and this exists in lots of different languages, in Ruby, Python, Java, TypeScript, even JavaScript, and of course Kotlin. In some languages, like I said, it would happen at runtime. In JavaScript, in TypeScript, in Python, which are more interpreted, you can essentially modify the behavior of whatever you want. In JavaScript, you can even change what the console.log does. In Java, Ruby, C, and of course Kotlin, you can modify things at compile time, which is much, much easier than doing things at runtime. And so we're going to look into it. But metaprogramming, like I said, is not something new. And it's not even something new for Android development. For Android development at the beginning, when everything was just Java and XML, we had something that was called APT, Annotation Processing Tool, which is something that's part of Java in itself. And the annotation processing tool basically could you read Java files, find annotations in those, and from the annotation would be able to generate some code. So you could actually have something where you put annotations in your classes, on your methods, on your fields, and automatically would generate some new Java code. And the new Java code would be compiled with the original one to make your application. When Kotlin came along, there was Kotlin KAPT, Kotlin Annotation Processing Tool, which mimics essentially what APT was doing. But instead of looking for annotations inside of a Java file, it would look for annotations in a Kotlin file. So it would still create Java output. And then Kotlin, JetBrains, created KSP, which is the Kotlin Symbol Processing Tool. And the Kotlin Symbol Processing Tool, again, finds annotations in Kotlin source file. But instead of generating Java code, you would generate a Kotlin file. And this Kotlin file would be, again, compiled against your own Kotlin file to have your whole application. The good thing about that is that because you're generating Kotlin and not Java, is that this is fully compatible with Kotlin multi-platform. And then you have, of course, Kotlin compiler plugins. And Kotlin compiler plugins is even more powerful than KSP, because now you're inside the compiler itself. And because you're inside the compiler, you have access to everything, not just annotations. You literally have access to everything in the code. And you can not only generate new things, but you can also modify the existing code that's being compiled while it's being compiled. And so again, because you're in the compiler, you're fully compatible with Kotlin multi-platform, which is amazing. And so you might ask yourself, why use a Kotlin compiler plugin? Well, metaprogramming and Kotlin compiler plugins in particular can be used for anything that is a cross-cutting concern. A cross-cutting concern is a piece of logic, something you want to do in the code that's not specifically tied to a layer of your application or a specific feature. It's not about just doing something that's going to be in the network layer or in the database or in the UI. It's something that's going to be everywhere in your application. And because it's everywhere, it's very hard to have a single base class that everything else is going to inherit from, right? So it's this little boilerplate code that you want to have everywhere, but you don't want to copy it everywhere. The usual example when we do metaprogramming is logging. You're going to have a way to automatically log stuff. And this is kind of the hello world when we're doing Kotlin compiler plugin. So we're going to see that today in those slides. But there are much more things you can do. And a few examples that might come to mind is, for instance, multi-threading. And that's what Coroutine does. Coroutines in Kotlin essentially will take your every statement in a suspend function and organize them in the way that they can actually be suspendable. So it's very interesting to actually look how they do it and what the bytecode in the end looks like when you're doing coroutines, because it lets you understand how it works and how it's actually not using threads. Power assert is another Kotlin compiler plugin that I really like. If you're doing any kind of testing on Kotlin, this is amazing, because when you're doing an assertion in your tests and the assertion fails, power assert is going to give you the actual value of all the variables and fields involved in the assertion and give you their current state when the assertion failed. Meaning that when your test is failing, not only do you have, hey, this test failed, but you actually know why and what was the value, and you know how to reproduce it. For serialization, there are lots of serialization to JSON, to XML, to any other kind of format that exists, and lots of libraries. A lot of them will either use Kotlin symbol processing or a Kotlin compiler plugin. And Kotlin X serialization uses a plugin to automatically convert any data class that you have into any format that you want. And finally, of course, Jetpack Compose is also having a plugin to modify your compose annotated methods into something that can actually create a UI. And it's going to also create all the boilerplate to remember your states and do all the state management for you. So we want to write a Kotlin compiler plugin, but first we need to understand the Kotlin compiler. We're going to start with a bit of history, right? Kotlin started in 2011, and at the time, the idea was to have a more modern syntax for JVM-based programming, right? And one of the goals was also to be able to have higher order functions, lambdas, that Java didn't have at the time. Very quickly, in 2012, it became open sourced, and then until it grew, and in 2016, Kotlin 1.0 was announced as stable. Then 1 year later, at Google I/O, it was announced to be officially supported for Android development, and Kotlin multi-platform was announced. A few years later, 2019, Kotlin became the preferred Android language, which is why I'm pretty sure most of you, if not all of you, are actually writing Kotlin today. Then Jetpack Compose started in 2021. In 2023, KMM, which is Kotlin multi-platform for mobile, so it's just a subset of KMP, was announced as stable. And a year ago, K2, so the latest version of the Kotlin compiler, was announced as stable. And nowadays, I think most of the IDEs, you still have an option to disable it, but most of the IDEs would use it by default. So now we know a bit of a history of Kotlin. We have a Kotlin compiler. How does a compiler work? If you think about it, you should have the basic idea. You have Kotlin source file as an input, pass that to the Kotlin compiler, and depending on your target, you're going to have either JVM.class that are going to be dexed into Android. You can have native SO libraries if you're targeting macOS, iOS, or Linux. You're going to have JavaScript if you're targeting the browser, or you can have WebAssembly. But that's really the bird's eye view of what's happening in the compilation. So let's dive a bit deeper. One thing to know is that in the Kotlin compiler, you have two parts. You have the front end and the back end. And on a very rough idea, you can think of the front end as the part dealing with the input, and the back end is the part dealing with the output. So in the compiler front end, what happens is that you have your Kotlin files as the input, and the first step that it does is transforming it into an abstract syntax tree. This step is pretty important because a Kotlin file essentially is just a text file with a .kt extension instead of txt, meaning that it's just a bunch of characters together that don't really mean anything. The abstract syntax tree itself will understand the semantic meaning of the code you've written. So if you have this kind of text of characters in your Kotlin file, well, this is what it's going to look like as an abstract syntax tree. You're going to have a function node that says, oh, I have a node name that has the value to string. I have a node's params that don't have anything because there's no parameters for this function. And I have a node return type that's going to have the value Kotlin.string. And the abstract syntax tree at the beginning just knows what's inside the file. It just says, I'm converting just to verify the syntax. Right? And then you have the rest of the compilation process, which transforms this abstract syntax tree into FIR, the front-end internal representation, which is something specific to K2, which will take the abstract syntax tree and make all the links that needs to happen between all the abstract syntax trees of all the files that you have, your own plus all the dependencies. And so what it means is that it's going to know that, oh, I'm importing a class that's in another file, and I'm calling a method on these. And I'm going to verify that when I call the method, the types that I pass in actually match the types that are expected in the method signature. Right? So this is where the compilation process that says, oh, yeah, my code is actually valid. It works. Or it's going to fail and say, hey, you're trying to call this method with an int, but it's expecting a string, or whatever. Once you have this front end, and you know, this step, by the way, is like there's 20 steps to go from the AST to the final front end internal representation. Once you have this, we pass that to the compiler backend, and the front end internal representation is then converted into the internal representation via a set of steps that are called lowering, where you essentially convert all of the syntactic sugar that you have in Kotlin. Right? So any templating in a string, you know, when you have a string where you can put $ with your variables and so on, it's going to convert that into a string builder or whatever is the equivalent for the platform you're targeting. It's going to take all the lambdas and convert them into something that matches the platform you're targeting, right? So if you're using something that exists in the Kotlin language but doesn't exist in JavaScript, for instance, it's going to lower that and convert that into something that can actually be written in JavaScript. And once it's done all these passes of lowering, then it's going to write either the jvm.class, the native SO, the GS file, or the WASM file. And so, like I said, you have lots and lots of steps. The good thing is that the Kotlin compiler allows you to hook yourself to any one of those steps to actually look at what's happening and the state of the code being compiled, or even modify it, right? So let's write a Kotlin compiler plugin. The boilerplate to write a Kotlin compiler plugin can be a bit daunting. Fortunately, there is a GitHub repository called compiler plugin template, which has a template for a compiler plugin. Right? It's written by JetBrains themselves, maintained by themselves, so it's pretty up to date. You can get it and start writing a plugin just right now. It's going to have 3 main modules. The first one is the plugin annotations. Plugin annotations is just you saying, hey, my plugin, you can use those annotations to modify what the plugin is going to do to your code, right? So if essentially, you can let users say, oh, I want your plugin to apply to this class, or to this function, or to this property. You can do that. Then you're going to have the compiler plugin module, which contains, well, the meat of your plugin. It's what's going to be actually run by the Kotlin compiler during the compilation process. And then you're going to have the Gradle plugin. And the reason that is because your compiler plugin is going to be a jar that needs to be passed to the Kotlin compiler, but the way to pass it to the compiler is pretty tedious. And so the Gradle plugin will say, hey, if I'm on a Gradle project, whether it's Kotlin.jvm, Kotlin.multiplatform, Kotlin.android, or anything else, I'm going to find the actual Kotlin compiler task, and I'm going to update it to actually use your compiler plugin. So everything is already set up. You can just use it out of the box. The template has a couple of examples of things you can do with a plugin, but then you can just add your own, of course. So what's the plugin entry point? This is the main thing that you want to have at the beginning. The first thing is that you need to extend the compiler plugin register, which is just to say, hey, this is me wanting to do something within the compiler. It has one property called supports K2. It was added a few years ago because while K2 was not stable yet, you could say, hey, I want to be compatible with K2, or I don't care. Usually, I would advise you to say it true, because nowadays K2 is stable, and this is the default that most programs are going to be running with. And then you're gonna override these register extensions, which is just to say, hey, these are the things I want to add to the compiler, and this is where I want to hook myself to. So you have, like I said, you have lots of places that you can hook yourself into and get a callback. The main ones that you want to extend are going to be the fur extension register adapter and the IR generation extension. The first one is essentially going to call you when all the passes of the front-end internal representation are done, and you have the fur that's ready to just call you. And so you have the fur in its final state, you can investigate it, and you can even add something to it. And then the IR generation extension is when the fur is converted into internal representation. But you have other steps. You have a step, for instance, whenever you want to convert from IR into a JVM class, and you have lots of other steps as well. I won't talk to all of them, but you can find them in the code. Now what? I have a plugin. I'm hooked into the compiler. What can I do with that? Well, the first thing that you can do is create diagnostics. Diagnostics, essentially, I think maybe most of you are going to be using detect to have static analysis of your code, which can allow you to investigate and look at what the code looks like and raise warnings or errors. Well, diagnostics is just that, but during compilation, right? You can modify, of course, the existing code, which is one of the great things you can do with the Kotlin compiler plugin, and you can generate new code. So let's dive in. Creating diagnostics, you're going to inspect the front-end internal representation because you're at the beginning. You're during the compilation process, so you haven't translated that into IR and then JVM or JS or whatever yet. And you can raise warnings and errors that are going to appear in the output of the compiler within Android Studio. So here's the goal. Here's what we're going to do. This is just an example, of course. The check not null, require not null methods. What did you can use, to have, verification at the beginning or in the middle of your classes or of your functions. The quote-unquote bad things about them is that they're going to throw an exception, and if you don't catch the exception, it's going to crash your app. So you might say, hey, I want to raise a warning or an error whenever we use those to say, hey, by the way, this can crash the app. Maybe it's not a good idea, or maybe make sure that it is caught by whatever function is calling them. And so what we want to do is whenever we use them, we're going to create an error, right? So to do that, we're going to extend this for additional checkers extension. As the name suggests, it's additional checkers to the one that fur already has. Right? Like I mentioned, during the fur process, you're going to verify that the types match the types are matching when you're calling a method, that you have all your nullability checks, and so on. You can add more checkers. You have the type checkers, which allows you to verify the typing hierarchy of a class. So when you have a class and say, oh, I'm extending this other class, or I'm implementing this interface, you can verify that. And maybe in your case, in your project, you say, hey, I don't want those two interfaces to be implemented by the same class, or have any of the checks you want. Declaration checkers allow you to verify the declaration itself. For instance, if you want to make sure that classes follow a specific naming scheme, or anything else. And expression checkers is you verifying any expression, any statement, any function call that you want. And this is exactly what we're going to do. In the expression checkers, in our own version of the expression checkers, we're going to create a function call checker function call checker. So function call is one of the expressions that you can check. There are lots of others, but you don't have to do them all. And we're going to create an unsafe call checker object. This unsafe call checker object will extend the first function call checker. That's a mouthful. And essentially what it does is it's verifying what's happening whenever a line in your code is calling a function, right? You can create an object that is going to be your diagnostic object. So this is the error or the warning that you're going to raise if need be. And then you can override the check method, which takes as the input the expression itself. And the expression is going to be a function call object. And then it's pretty easy. I won't go into the detail, but you can verify, is my expression valid? So you can look into the expression and say, is it the check or check not null, or is it the require or require not null method? And if it is, then you're going to return true, it's invalid. And from that on, you can call on the reporter object the report on function that takes the diagnostic, of course, but also the expression.source. And expression.source is something that's really amazing because you're still in the front end part of the compiler, meaning that the front end deals with the input. You still have the link with the source. And so expression.source not only knows which file this expression comes from, but it also knows the line, meaning that when you create a report in your IDE, in Android Studio, you're going to see, hey, you have this error in this file at this line. This is going to look like something like this. When you're calling it, you're going to have, hey, require not null can make your application crash and must be avoided. And it's on the main.kt file on line 9. And the next error is on line 11. So when you click on this error, you actually go where you want to be. If you want to go further with this, you can also use annotations to let the user say, hey, by the way, I know I'm calling check, but that's OK. I verified it. So you can have an annotation to say, hey, if this function is annotated, I don't need to go and verify if the check or require is being called, and you can just bypass that. The good thing with those diagnostics, like I said, is it happens during compilation process. So it can happen silently while you're coding. And so you don't have to wait until you're making your pull request, and then you have your CI that's going to call detect, and then come back 5 minutes later to say, hey, by the way, you have an error here. Here it's happening while you're coding. So you don't necessarily have to do all of the detect checks or all of the checks that you can think of in the compiler plugin, but if there are some that are very important and that come back a lot during code review, then you can make it in a plugin diagnostic. Then we can do code modification, where we can manipulate the code inside of the IR extension. The idea here is that, let's say we have a method fun do something that takes an int and a string. If we annotate it with the @log method, which is one annotation we created, it's going to become, in the compiled version, the same function, but with a print statement that says, I'm entering the do something function with those arguments. The way to do it, so it's going to be a bit more complex, but essentially you're going to create a visitor. The IR extension uses a lot of visitors. The idea is that the visitor is going to visit all of the nodes in the IR tree. And so you're going to have a visit class declaration, visit imports, visit property declaration, and so on. And of course, you're going to have a visit function. This visit function is going to take the function that you're actually visiting, the one that we're interested in. And so the first thing you can do is verify if it's annotated. That's one of the goals. If it has, so you can look at the declaration.annotations and verify if any of them has the actual right name. FQ name, by the way, is something that appears a lot in IR and FIR. It's fully qualified name. So it's the name of the class plus the package that it is in. And for a function, it's the package, the class, and the function name. If it's annotated, then I'm going to wrap the body. So essentially, I'm going to replace the declaration body. So everything that's in the curly braces of the function, I'm going to replace it with the output of this wrap function that I'm writing. Right? So essentially, I'm modifying the code. I'm saying, oh, you had a body. I'm replacing it with something else. This wrap function is pretty simple. I'm just creating a new body. And inside of the body, I'm just adding this log fun start So we're going to see just next what it is. But we're going to say, I'm adding one call, one expression at the beginning. And then for all of the statements in the original body statement, I'm just going to add them as they are. So I'm not modifying anything else, anything of the code. I'm just adding something, a little something at the beginning. The little something at the beginning looks like this. It looks a bit daunting, but don't worry, we're going to go through it. First thing we do, we create a concat node. And the concat node is essentially just concatenating strings. Right? It's part of the code you can use in the compiler plugin. And first thing we're going to do is we're going to add an argument. We're creating a string. So our string is just saying, I'm creating a string, a hard-coded string. Fun thing is, in the compiled code, the string is going to be hard-coded, but here we can still use templating. So it's going to be a hard-coded string with the arrow and the actual function name. But here in our compiler plugin, we can just create it the way we want. So we start with concatenating a arrow with the function name and open parenthesis. Then for every parameter of the function that we're creating, we're going to have first a comma if it's not the first parameter that we're writing in. We're going to have an hard-coded string that says the parameter name with the equal sign. And then we're going to add arget plus the value parameter. So essentially, we just say if our parameter is called I, you're going to have in a string I equals, and then plus I. So we're going to get the value, the actual value at the moment it's being called of the parameter. Next, we just add a hard-coded string with a closing parenthesis. And what we're going to return is a function call for the println function, where we replace the first argument with the result of this concatenation. Right? So this is exactly what we wanted to have. And so if we had this getAgeAsString method that returns my age, years old, whatever, and it's annotated with the log method, well, when we run it, it's going to actually print, hey, I'm entering this getAgeAsString with, well, there was no argument, but it also includes the automatic argument with this, which is which object this is called on. Here you can also see that in my example, I didn't add it in the slides because this would be too long, but I also would say I'm exiting the function, and this is the value I'm returning, which can be also very interesting to see. So, generating new code, this is going even deeper, but essentially you would declare the new class and functions in the fur part of the extension, and you would inject the function body and the statements in the IR extension. So you need to do that in 2 steps. I didn't integrate a sample for this, but actually there is one in the template repository that I mentioned, so you have everything in there to know how it's done. One of the drawbacks with just generating code, new classes, new objects, new fields in the Kotlin compiler is that it only exists in the compiler itself, meaning that the IDE is blind to it. So in the IDE, in Android Studio, when you're doing that, you're going to have red names all over because Android Studio doesn't know yet what it is, even though it's running perfectly in the Kotlin compiler. So one thing I would advise is if you can use just KSP, Kotlin Symbol Processing, to generate your new code, because it's going to generate a Kotlin file that's going to be in the build folder, and your IDE can actually know where it is and understand it, and so it can resolve it, and you would have code completion, which is pretty useful. Next, we need to talk about testing. Testing is important, and even when you do metaprogramming, you need to do some tests. The great thing is that testing for a Kotlin compiler plugin is very, very easy because there is an automated framework, and it's actually, again, part of the template repository that I mentioned. So you can just, the boilerplate to test a plugin is already done. In addition, JetBrains also has this Kotlin compiler dev kit plugin for your IDE to simplify finding all the data for your test inside of the IDE. The way it would work is that you would just create the file that you want, a sample file that you want to compile, and that would have some of the assertions. So for the diagnostics, for instance, we would have this kind of file. The first thing is run pipeline till frontend, which says, OK, I know that because this is a diagnostic, it's going to raise an error if we pass the front-end part, the front-end internal representation part. So I'm saying, just run the compilation until the front-end, and then we pass in the testing mode. Then you're going to have your code. And one of the things that you can find, that you can see, is that there is this check call between those angle brackets. Essentially, it's just saying, hey, by the way, this expression is going to raise an error, and the error type is going to be check call. And so essentially, when you run your code, if no error is ran or is raised, you're going to have an error, and the test is going to fail, right? In addition to that, you can also have another type of testing to say, hey, by the way, I want to make sure that if I have this annotation, allow unsafe calls, like I mentioned, I want to be able to call the check method. And of course, this is just 2 functions, but you can have more examples in your test to test all possible use cases. Testing code generation is also very, very easy, because every file.kd that you have in the test data is going to have generated a file.fur.text and file.fur.ir.text, which are the fur and ir representation of what's in your source file, in your test file. Meaning that if you have, for instance, this log method .kt, then we say, hey, I want to test this at log method. And you have this, you have a bunch of comments that you can have at the top to say, look, here I'm to say I'm also using the standard Kotlin standard library. The first time you run it, it's going to automatically generate the fur and ir text files next to it, and then you can modify those to say, hey, this is what I want to have. So the fur.text will look like something like this. So you have the front-end internal representation of your code. It's a bit verbose, but it's very, very close to what you have in your code, right? Because you're still in the front-end part, so you're still very close to the source file. The ir file, it's going to be trickier, right? Because you're very, very close to the metal, right? It can be, it's verbose, it's hard to read because we're not used to it, but actually, if you look into it, it starts to make sense after a while. And so when you have those files, well, essentially you can say, OK, no, I'm going to change the IR to say this is the IR I should have at the end of the compilation process. And then when the test runs, essentially, it's going to run front-end and IR on your test data, and then compare the output with the one that you have, with those files that you have in your test folder. If you want to go even further, well, first of all, we can talk about compiler options. Compiler options is the ability to say to the compiler plugin, hey, by the way, I'm going to add an option. For instance, the @log method that we had earlier, that we made to println everything that happens. You might want that in debug, because you're working, you have the eye on the console, on the output, on logcat, so you want to see what's happening. But at runtime, in production, you don't want that. So you can say, hey, I'm going to have a flag in the compiler option that says, oh, by the way, turn it on or turn it off. Or you can have something that says, oh, if the function is in this package, ignore, or whatever. So you can have everything. The inputs, you can have files, you can have any primitives. And you can also adapt the Gradle plugin to say, oh, by the way, I'm going to have a block that people can use. So yeah, they can have that. You can have my plugin in your Gradle file and pass in the options, and the Gradle plugin will then pass that to the compiler. Again, there's an example of that in the repository that JetBrains made. There is this IDE plugin which is also amazing. It's called Fur Tree. And what it does is basically it's creating the tree of front-end internal representation of the file that you have opened. And also it links the nodes to the lines. So when you click on the node on the left, it's going to highlight the line that it refers to on the right. So if you're making a plugin and you don't really know what's going to be the kind, the type of fur objects or IR object, you can look at this and it's going to give you exactly what it is for this class. So you can write a sample code and then it's going to give you how it looks in the compiler. Finally, here are a list of other plugins that I really like and that you can also go look at. They're all open sourced, meaning that you can go in there and look how they actually wrote it, or just use them in your code. The first one is called Mockery. It's a mock plugin. If you do any kind of Kotlin multi-platform testing, lots of mocks projects are JVM oriented. This one is pure Kotlin multi-platform. It works on any kind of target, which makes it amazing. I use it in some of my pet projects. Really encourage you to use it in your test. The fun cache is memoization in a compiler plugin. So automatically, it's going to create caching for functional results. Pretty useful. Poco is going to generate the equals and toStrings on annotated classes, kind of like what data classes do. Problem with data classes is that they can't have any complex hierarchy. Right? So if you have a class that needs to have a complex hierarchy, you can still use this to generate an equals and toString and hashcode methods. And then inject, as the name suggests, is a dependency injection that's built at compile time. And that's pretty useful as well. And yeah, we're down to the last few minutes. Thanks a lot, everyone, for your attention. And if you have any question, I think we have a microphone up there, or you can just come and see me after the talk. Yeah.